renewable energy sources. We talked about fossil fuels. Today he's going to get into the nuclear energy issue. And I'm going to give him to you right now. Dr. Snyder.
Fellow nuclear scientists, well, soon to be anyway. Today we're going to talk about nuclear science and nuclear reactors and energy. And this is just a touch complicated, not too complicated, but a little bit. And the only thing you're going to notice is that there's going to be a lot of "it turns out," because I can't really go into the details of how everything works. But it's all there on the internet or wherever you want to look. And it's not that hard. So all of this depends upon Albert Einstein's observation in 1905. First, he observed that time was money, which is an axiom that has withstood the ages. And then he observed that energy was mass. And the idea here was not that you can burn mass like firewood and get energy. The idea here is you can take mass and totally annihilate it and convert it directly into energy. No mass left whatsoever, no ash, no nothing. Total energy. And the formula, as we all know, I hope, is E equals mc squared, which means that the energy is derived from the mass by multiplying it by the speed of light squared in appropriate units, and the speed of light is huge. It's 300,000 kilometers per second, so a big number. As an example, if you took 1 pound of matter and totally converted it into energy, you would get roughly 11.4 trillion kilowatt hours of electricity. That's a lot. Another example, if you took a teacup of seawater and put that through a fusion reactor and had 100% burn, so you converted it all to energy, you would get the same energy equivalent as burning a ton of coal. So clearly a very dense energy form. So to understand how this applies, we have to know how the atom is put together, and this is sort of the end of the science part, the beginning and the end quickly. And we're going to actually work with a model of the atom called the Rutherford atom, very primitive, dates from about 1913. Rutherford was a scientist who liked his physics, and he's responsible for a aphorism: all science is either physics or stamp collecting. He was somewhat arrogant in that view. At any rate, how this atom works, by about 1860, for those who have studied a little physics, Clerk Maxwell knew that electrons charge, negative electrical charge, which is what formed currents, came in little discrete units, which they called electrons. And we knew that atoms were made up of shells of electrons around the outside and some sort of positively charged material on the inside. And they had to balance because atoms were neutral, so the same amount of positive charge and negative charge. And we didn't quite know how it worked. And Rutherford shot some particles into a gold foil, and some of them rebounded, which, as he said, was like firing a bullet at a piece of Kleenex and having the bullet bounce back at you. Quite remarkable. And it led him to believe that the interior part of the atom with the positive charge was isolated in a little spot in the center, which was called the nucleus. And the model is that if you think of the atom as a basketball with the electrons on the outside, the positively charged nucleus is about the size of a grain of rice in the center. And it can also have in the nucleus some other things called neutrons, which have no charge. They can't have any charge because the charge has to balance the positive and the negative. But there are these neutrons in the center, and that makes up the model. Now, quickly, there's two things obviously wrong with this model. One thing is that if you have electrons going around the outside, even Maxwell in 1860 knew that they would radiate. That's how radiation takes place, so moving electric charges. And so when they radiate, they lose energy and they spiral into the center, and the Coulomb force, opposite charges attract, would collapse all the atoms. So we know that can't be right. And the solution to that is what's called the quantum theory, which started in the beginning of the 20th century and is now pretty well understood. And we also have a problem with the nucleus, because you got all these positive charges stuck together, and we know that like electric charges repel by Coulomb's law. So the nucleus shouldn't be stable, it should fly apart, and it doesn't, which led to the concept of the strong force and what is called hadron physics. So both of these problems have been solved, but we're still going to work with that model, and it's really good enough for our purposes. The neutrons can come in varieties of numbers. So for example, for hydrogen, which has one proton, and the number of protons determines what the element is. So hydrogen is element 1 in the periodic table that you see in your classroom, and it has one proton. But it can have no neutrons, which is regular old hydrogen, one neutron, which weighs about the same as a proton, and is largely all the mass of the atom, because protons and neutrons both weigh about the same. They weigh about 1,830 times as much as an electron, so you can ignore the electrons. And that's called deuterium, for 2. And 2 neutrons with a weight 3, still hydrogen, because it only has one proton, which is called tritium. And that's useful in fusion physics, which we'll get to in a minute. So the number of protons determines the element. 2 protons is helium, right, the second element, and 3 is lithium. And if we skip all the way down the table, 92 protons is uranium. And uranium turns out to have some interesting properties. It can have roughly 140 neutrons, and the different forms of uranium, which are called isotopes, just depending upon how many neutrons they have, range from U-233, 233 is the mass, which is the total number of protons, 92, and neutrons, up to U-239. And it was found in about 1939 by 2 German scientists that uranium could be split in half by appropriately firing some neutrons at it, some energetic neutrons. And when you did that, the 2 halves, you added them up and weighed them, and you weighed the other debris that came out of the splitting, and you'd lost some mass. And lo and behold, you got a lot of energy, and it actually obeyed E equals mc squared, exactly. So there was a clue, and it turned out that one isotope of uranium had a remarkable property, and that was that when you fired a neutron in to split it, just this one isotope, you got out some debris, some energy, and you got out either 2 or 3 more neutrons, depending on how the thing split. This led to the idea of a chain reaction, that you could start this thing, and it would keep going by itself, because it would generate more neutrons every single time it split, and it would take care of itself. So you could think of this whole stage being covered with mouse traps with ping pong balls on the bales, and I flip a quarter in there, and pretty soon there are ping pong balls in the air like crazy. Everything goes off. And that's essentially the idea of an atom bomb. Now, I want to describe an atom bomb very briefly, just because I want to convince you that a reactor can't be a bomb. A reactor can be a mess. It can be a horrible chemical explosion. It has its problems, just like every other kind of energy has its problems. It can't be a bomb. So the bomb's very simple. All you got to do is have a large enough mass of U-235 so that the neutrons coming out, which are coming out very fast, about 1/15 the speed of light, don't just fly through this mass and go out and miss everything. They've got to have enough mass, enough size that they hit things. Size turns out to be about the size of a basketball, which is called the critical mass. And so all you got to do to make a bomb is you got to get U-235 and make a thing the size of a basketball and wait for a neutron to hit it like a cosmic ray or something, and off you go to the races. Now, of course, it's not quite that simple, because you don't want to drive around with that in your car or fly around with that in your plane. So what you do is you make 2 pieces that are about half the size, keep them far apart where they can't interact, put a little conventional explosion behind each one, put in a barometric fuse that sets it off by pressure, drop it out of an airplane. When it gets low enough, the fuse goes, it turns on the conventional explosions, jams those two halves together, and now you have a critical mass, and there you are, Hiroshima. Only 2 such bombs have ever been made and set off. One we set off in the desert, one we set off over Hiroshima. All other bombs ever done, and now all bombs are made of plutonium, which we'll get to because it's much cheaper. So that's how a bomb works, and people thought after this, why not use this for energy in a controlled way? Now let me just back up 1 second and say, you're getting U-235, the reason we don't make bombs out of U-235 is very expensive. U-235 is very rare, and when you mine uranium, which is called yellow cake, you get 0.7% U-235, and the rest almost all is U-238. And the way you separate those, which is expensive and time-consuming, the easiest way, I guess, is centrifuging. There are a number of ways to do it. You convert it to a gas, uranium hexafluoride, and the U-238 hexafluoride weighs a little more, 3 neutrons worth more than the U-235, right? And you put it in a centrifuge and you spin it, and the heavy stuff goes down and the light stuff's up here, of which there's very, very little, 0.7%. And so you bleed that off and you stick that in the next centrifuge and you do it again. And you keep doing it, which is called cascade centrifuging. And at the end, you get some pretty pure U-235. But it's a long and expensive process. And there are easier ways to solve that problem. Now, to make a controlled reaction, what you have to do is make sure, A, you don't have a bomb on your hands in your backyard, and B, that you have some way of controlling the amount of reaction going on. So what they do is they, first of all, you got to slow the neutrons down if you want them to stay around enough to react. So you have to use what's called a moderator and put your reaction in a moderator. We use water. Some other people use graphite. Chernobyl used graphite, which proved to be a mistake. That wasn't what caused it, but that was part of the problem. So you have this water, and the water serves 2 purposes for us. You remember that any energy reactor, power station, coal, gas, whatever, all it's doing is heating water, right? So if you have a nuclear reactor, you got to heat water eventually. So you can use this water both to make the reaction work, which is the moderator, and the same water can be used for getting the heat out to a heat exchanger. So one other thing, when you see those big hyperbolic cones on the ground, you drive by and say, those aren't necessarily a nuclear reactor. They have nothing to do with it, per se. They're cooling towers. And you can't get all the heat out of the water. If you want to reuse the water again to pick up more heat, you got to get the water cooled. And those towers could just as well be a coal-fired power plant as a nuclear-fired plant. So what we do is we take this uranium-235, we enrich it to maybe 4%, not bomb grade, 95%, but 4%. And we put in a very, very thin rod, most of which is 238, 4% is 235, and we stick those down in the water and we have them spaced far enough apart that just enough of the neutrons hit each other to keep the reaction going in a reasonable way. And to control it, fine-tune it, we have these absorbing rods we can push in and out. This is how the old-fashioned reactors work, and this is how all our reactors work, 104 of them. They're all old-fashioned. Even the ones we're building today are old-fashioned, unfortunately. And you push these rods in and out, and you can control the reaction. Things that can go wrong, you can lose your water. Well, that's a problem because then things do heat up and there's no cooling to take the heat away. Incidentally, how does the water get hot? A lot of the neutrons fly off and don't hit anything, and they go into the water and they slow down, just the way putting the brakes on in your car generates heat on the brake pads, right? So the neutrons go into the water and slow down. They give up their energy to the water, and that's what heats the water. But you can never have a bomb this way. You can have various things go wrong, just as with any other kind of energy, but never a bomb. So now the biggest problem with this is that there's waste, which now is no longer called waste, it's called used fuel, euphemistically. The problem is this: you've got these neutrons running around splitting things apart. You can split anything apart. It's just that U-235 has the great advantage of giving you more neutrons. But what about the 96% of U-238? Well, that can absorb neutrons, and it does. And it becomes U-239, absorbs a neutron. Still uranium, still 92 protons, but it's unstable, and it decays into neptunium, which is the next element, 93. And what happens is that one of those neutrons becomes a proton and an electron. So you have one more proton in the center, so the atomic number goes up one, you have one more electron to balance it. And that hangs around for about 22 days or so, half-life, and then it decays again, and it becomes plutonium-239. Plutonium-239 is an interesting material. It's man-made. There's some remnants of it on Earth, but almost all of it is decayed away. It's weapons-grade material, too, and it's cheap to make from the waste. You can take it out of the waste by, I hate to say high school, but high school chemistry, using robotics, because it's very radioactive and nasty stuff. And that's why a lot of people like to run reactors like North Korea. You think, why do they want to run a nuclear reactor? You know, well, they want the waste. And they take plutonium out of the waste, and then they make a bomb. The good news is that the plutonium bomb is very hard to detonate. The trigger mechanism is extremely sophisticated. And so the tests that North Korea has done of their nuclear weapons have yielded 2 or 3% maybe of the potential yield. They're not doing too well with the trigger mechanism, and there's no expectation that they will. So that's essentially how a fission reactor works. As long as it's running right, no problem except the waste. And we'll try to talk about the waste quickly in the remaining 30 seconds. No, I didn't quite that bad. So fusion, let's talk about fusion for a second. Fusion is how the sun works, which is a nuclear reaction too. And fusion, you fuse light things together. And the sun, at about 10 million degrees centigrade, fuses hydrogen into helium. And if you weigh the parts, the same old story, there's some missing mass, E equals mc squared. There's enormous energy, as we know, because the sun has been working for a long time and puts out lots and lots of energy. Fusion, here's how it works. You want to heat up the hydrogen to try to get it to fuse, and you got to force it to get together because the centers, the protons in the center, the nucleus, are similarly charged and repel each other. So what you do is you like to heat it up, but you want to keep it around. You don't want it just to fly away. So you like to put it in a box and heat it up. The trouble is 10 million degrees centigrade, there's no box made that's going to hold that. It just melts the box, vaporizes it. Fortunately, when you get it hot enough, the electrons strip off and the material becomes what's called a plasma, which is free protons running around and free electrons. And they're very susceptible to a magnetic field. So you could build a magnetic bottle. And if you build a magnetic bottle by putting a magnetic force on the electrons, of course what happens, if you know some physics, is you put a magnetic field on an electron and it shoots it out to the side. So they'll all disappear. So what you have to do is build a circular affair so that when it shoots it out to the side, it shoots it around a raceway called a torus mathematically. So almost all the plasma machines are toroidal geometry, and they're almost all based upon a Russian design called a tokamak, which means in Russian, sorry, we invented it first. But they are all built on tokamaks, and we're building right now, a consortium of 7 nations, including the European Union, an enormous fusion machine in Cadarache, southern France, down by Marseille, to show that this could be viable as an energy source. When this first was proposed by Teller after the Manhattan Project, they said that fusion and power would be too cheap to meter. 50 years later, the joke is too expensive to matter. It's a very expensive kind of energy, but it holds tremendous promise, and I think someday it will be it. And that's all I'm going to say about fusion for the moment, except we do have fusion machines, and they work fine, and they produce neutrons. That's what fusion does. It fuses hydrogen into helium and produces neutrons. And that's how you make the reactor work, same as with a fission reactor. The problem is that it costs more to run the machine than you get out of it in energy. It's not an energy machine, but it's a perfectly good fusion machine, and it produces neutrons, and lots of them. Just costs you money to run it. But I mean, so does a chainsaw, so does a railroad engine. They cost money to run too, but we find them very useful. And what you could do here to get rid of the waste, because all the waste can be split into things that are much less harmful and long-lasting, but you need neutrons to do it. Now, with U-235, you keep making your own neutrons. With other things, you got to, like plutonium, you got to make your own neutrons. And, well, not plutonium, any other example, americium. You got to make your own neutrons. So if you took this waste and wrapped it around a fusion machine and ran the fusion machine just to make neutrons, you could break down the waste, which is called a hybrid reactor, which doesn't exist yet, but everything is there on the shelf to make one. And you would get a ton of energy out of doing that. If you got 4 units of energy out of burning the rods in a reactor for 5 years originally, you would get 1 more unit of energy net from running the hybrid reactor and get rid of the waste. So just a quick word about what we do with our waste. The government recognized at the very beginning with the first reactor, which was built in Pennsylvania, that waste was a problem. And so the government said, we'll take care of the waste in their infinite wisdom. And they arbitrarily decided to charge all the nuclear utilities 1/10 of a cent per kilowatt hour. And that fund got up to $37 billion before we had the good idea of burying all the waste, instead of putting it in the swimming pools around reactors, burying it all in Yucca Mountain, which cost $14 billion. And we decided not to do that. Just $14 billion. So the waste fund is not quite as big as it was. And President Obama appointed the usual blue ribbon panel, which is how we decide in this country how it is best to proceed, what to do with the waste. And the blue ribbon panel reported back about a month ago, and the answer was shovels for everybody, find another hole to dig and put the waste in it. So that's where we stand on the waste at the moment. And the waste isn't that bad, really. We have about 500,000 tons, but the uranium is very, very dense. It's 70% more dense than lead. And if you put all this in barrels and stuck them all on a football field, the whole thing might be 30 or 40 feet high, and that's all the waste there is. That's it. So it's not like it's an insurmountable problem, but it's a nasty problem. And you can get plutonium out of it and make bombs very simply, so that's a bad thing. So let me just summarize here, just for 1 minute, about possible solutions to some of our problems. I want to first say that everything has problems. As we noted, coal, according to the EPA estimates, coal alone, aside from mine disasters and things like that we see on television, just by breathing the air causes 30,000 deaths a year. And natural gas has fires and explosions. There was just in the paper a settlement, $18 million or something, with some group in Texas where they blew up half a town with some gas fire. Oil, I mean, we don't want to forget the Gulf of Mexico. Oil does have its problems. And I want to just give you one quick funny statistic, not so funny, but about hydroelectric. We talked last time about Lake Powell, which took 17 years to fill behind the Glen Canyon Dam. Dams sometimes break. For example, in 1899, the dam of the Johnstown River Dam reservoir broke, and the water came rushing down and killed 2,200 people in Johnstown. And lest you forget that, when you are all old enough to buy alcoholic beverages, you will find out that in the state of Pennsylvania, you pay an additional 18% on every bottle of alcoholic containing beverage you buy for victims of the Johnstown flood in 1899. It's a good thing. Now, if by chance Lake Powell, the dam broke, the water would rush down the Colorado River, and the next thing down there is the Hoover Dam. And in case you were standing out there with your camera taking a picture, that wall of water coming from Lake Powell would be 235 feet above the top of the Hoover Dam. So that's a problem too. So everything has problems, and they have to be weighed. I think the problem with nuclear is that we can't see any of this stuff. They talk about, you know, radiation in the air. I mean, it's like flying on a plane. I don't get much worried by bumps in the road, but I do get worried about bumps in a plane for some reason, and you can't see any of it. You don't know what's out there and what's going on and what's going to happen next. And I think the feeling about nuclear is much the same. You see a fire burning, I mean, you sort of know what it is, and there are firemen on their way and stuff. You hear that there's radiation in the air. I mean, what do you do? I think that's part of its problem. So the solution I would propose, and then we're going to see your solutions. My solution is to get rid of oil. Most oil is used for transportation, and convert all of our transportation to natural gas. A lot of the world is already doing this. In fact, we're starting to do this. Just since the last time we talked, Chesapeake Energy has announced a partnership with 3M to build new tanks to hold compressed natural gas in residential vehicles, passenger cars, and a joint venture with General Electric to build compressed natural gas filling stations more efficiently for residential cars. And get rid of coal, and do that by converting to nuclear, and that's very expensive. But I would point out that there are sources of funding available. The simplest source is to put a $1 tax on the equivalent of gasoline. Does anyone want to hazard a guess what that would raise a year, a $1 tax on gasoline? $54 billion. So if you got more sensible about building nuclear reactors and built them in a different format, you might be able to build 8 or 9 nuclear reactors a year and replace coal reactors. You could put them in the same place. All you're doing is heating water. The distribution system and generators and stuff, they don't know where the hot water comes from. So you don't have to start from scratch. So that's a suggestion. I think the government has to be involved in this because these are big problems, and they're too big for free enterprise and the marketplace to deal with. Much too big. So why don't you all vote on what you think might be your solution to this, and we'll see how we end up. Everybody has their own ideas. Hopefully now we all have a common set of facts. And I'd be happy while you're doing that to answer any quick questions anyone has. I'll try to anyway. Nagasaki bomb, like every bomb except Hiroshima, was plutonium. Yeah, and actually what caused the end of the war, the first bomb that was dropped, the Japanese sent scientists to Hiroshima, and from the debris they could tell that the bomb was a uranium bomb, and they advised the emperor that we probably would not have enough material for another uranium bomb because it was so difficult to make, and they were right. The second bomb was plutonium, and when they found that out, they advised the emperor to surrender. And we had out of Hanson in Washington State your plutonium manufacturing capability of an additional bomb every 12 days at that time. Anyone have a more friendly question? No, that was a friendly question, but anything that isn't about bombs. I can't see because of the lighting. If anyone up top has a question, you'll have to shout out what's your question. Yes. Well, I'm sure it will, but we have our own supply is the first issue. The supply market isn't nearly as tight as it is for oil, which is extremely tight, and it puts out half the CO2 per burning unit that oil does. So it's a much more greenhouse favorable solution, and I'm sure the cost will go up. But it's something we can control, whereas now, as we have noticed, I hope, we're sort of at the mercy of other people as far as controlling both the supply and the cost of petroleum products. So I think it's a plus. Yeah. 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 Yeah, that's a very good question, and it's a very complicated question. Oh, okay, that's a good question. Yeah, but it is a complicated question, and I would suggest some partial answers. One partial answer is that oil comes in varying qualities, just like coal does. For example, Venezuelan oil is very, very thick. It's almost what's called bunker grade oil, very hard to refine, and consequently quite cheap. The Texas oil is probably the highest quality oil, but there isn't that much of it. There's also an issue of taxes, and we have artificially controlled the energy market in America almost since its inception. And you can look at the cost of oil and you can look at the cost of natural gas, and both have been dramatically controlled through taxation and incentives and legislation. And all of that contributes to these disparities. And none of these things are genuinely a world market yet. They're getting there, but I don't think any of them are genuinely an open world market. And as far as being dependent, I mean, we are dependent in the sense that we need more oil than we can possibly produce. Not just what we are producing, what we can possibly produce. And we have to import that, and we have to import it from people whose political views are different from ours. And that's a concern, I think, that people may let their political views influence their business decisions. Oh, yeah. Oh, I'm sorry. This is beyond me. This is real rocket science. Any other questions while we're doing this? I'd be happy to take a shot. Yeah.
What would be your educated guess at how much money would be sunk into infrastructure for natural gas filtration?
There have been a number of guesses about that, and I think the guess is $100 to a couple of $100 billion, which sounds like a lot of money. But bear in mind that the big 5 oil companies last year had net profits of $139 billion combined. And so if they were involved in this, which I think would be a good choice if the government spearheaded a group with them involved, and they were allowed to buy out the infrastructure and operate it after it was operational and running, that would be an investment they could afford to make. But it is a big investment, there's no doubt of it. Are they answering these questions? Oh, I see. Okay. Oh, I can see this right here. So you guys like solar and wind? See, I like solar and wind too. It's just that I think solar and wind has a limited usefulness. Right now, Germany has said no more nuclear power, if you have read about that. And Prime Minister, I guess she is, Merkel, is under some real heat because she set the standard for 35% solar and wind in 10 more years, which I don't think they'll ever make. I don't think it can take care of base load. I think their real hope is to buy nuclear-generated electricity from France, which France is happy to sell them. But she's taking some heat now that she hasn't set up a program fast enough to convert everything to renewable energy. I don't think there is such a program. We'll see. That's just my feeling. But I would encourage anybody that can use renewable energy to use it. I mean, why not? It's a terrific thing. It's just that it's not going to provide electricity for New York, I don't think. Maybe we should just let New York go black. I guess not. They're saturated.
One more question we're going to answer.
Oh, okay.
So your choice is where should the government invest most of its energy budget? Which of those 4 areas?
Hey, I agree with that. I think that natural gas will take care of itself, and I think alternative energies are great, but they're not worth all of us investing in. A friend of mine put $40,000 of solar panels on his barn roof, which all of us paid $21,000 for in subsidies, which he got back right away. And he uses that electricity generated from his barn roof to power his all-electric car. That's great. It's just I don't think I should pay for it. You know, and the government doesn't need to pay for that. That's a sensible thing, and it will work fine. Nuclear is the answer. There's no way. Well, there are ways, but it's very tough to imagine private industry doing the whole nuclear heavy lifting. Plus, nuclear is regulated by the government, and the government really has to be involved in that if they're going to regulate design and construction and use and waste and everything else. So I think you guys are on the right track here, and obviously you were listening.